Most people walk across deserts thinking they are empty. But deserts are not empty, they are exposed. They strip the earth down to its memory. And when you understand what the ground is quietly revealing, you realize something remarkable. Gold, silver, and platinum do not hide randomly. They follow symmetry. They leave patterns. And deserts, more than any other landscape on Earth, reveal those patterns clearly, if you know where to look. Gold, silver, and platinum are often treated as separate metals, born from different worlds, valued for different reasons. But beneath the surface, they are connected by the same geological forces: pressure, heat, fluid movement, and time. In deserts, those forces are no longer buried beneath vegetation, soil, or water. They are written directly into stone. Dry climates preserve geological truth. Rain does not wash it away. Plants do not cover it. Erosion works slowly, honestly. And this is why some of the world's richest precious metal discoveries were not made in forests or valleys, but in places that looked lifeless. Gold forms when hydrothermal fluids move through fractured rock deep underground. Those fluids carry dissolved metals, rising slowly until pressure drops and the metals are forced out of solution. Gold settles first, heavy and stubborn, locking itself into quartz veins, shear zones, and fault lines. Silver often travels with it, but farther. Silver remains mobile longer, spreading outward into surrounding rock, staining the earth subtly. In desert terrain, this silver does not rot away. It oxidizes. It turns stone faintly gray, green, sometimes blue-black. Not bright, not obvious, but consistent. Platinum forms even deeper. It originates in ultramafic rocks, ancient magma bodies that cool slowly beneath the crust. Over millions of years, tectonic movement pushes fragments of these rocks upward. Deserts expose them. Dark, dense stones, heavy underfoot, often ignored. Yet these rocks tell the same story: extreme pressure, ancient origin, and metal concentration that cannot be recreated. In deserts, the absence of soil becomes an advantage. You can see fault lines clearly, long, straight scars cutting through rock. These fractures are not random. They are pathways. Gold loves pathways. Silver follows them outward. Platinum hides near their roots. Quartz becomes a language here. White quartz veins cutting through darker host rock are not decoration. They are evidence, especially when the quartz is fractured, iron-stained, or broken. Rust colors are not decay. They are oxidation halos, the ghost of metal that once moved through that stone. Desert quartz often looks ugly, cloudy, broken. Veins that seem worthless. Those are the dangerous ones, because perfect quartz rarely carries value. Broken quartz means movement. Movement means opportunity. Silver announces itself differently. In deserts, silver often appears where rock looks slightly wrong. Darkened patches, greenish tints, stones that feel lighter than expected. Silver minerals oxidize near the surface, and the desert preserves those oxidized skins like fingerprints. Platinum is quieter. It does not stain brightly. It does not sparkle. It hides in heaviness, in rocks that feel denser than they should be, in black sands left behind after wind removes everything lighter. Desert washes, dry riverbeds, are critical here. Even without water, gravity still sorts material. Heavier metals sink. Over time, wind replaces water. The same physics apply. Platinum, gold, and sometimes silver collect in subtle traps, behind rocks, in bends and depressions, where motion slows. This is symmetry in motion. Gold settles closest. Platinum settles deeper. Silver spreads wider. Different behaviors, same rules. One of the strongest desert indicators is repetition. One strange rock means nothing, but a pattern means everything. Quartz appearing again and again, rust colors repeating along a line, dark, heavy stones clustered unnaturally. Nature repeats what works. Deserts allow you to see repetition without distraction. And this is why modern prospectors often fail. They search for shine instead of structure. They chase surface glitter. They ignore geometry. But geometry never lies. Straight lines in nature are rare. When you see them, they matter. Faults, veins, contacts between rock types, boundaries where pressure once changed. Gold respects boundaries. Silver leaks across them. Platinum anchors below them. In deserts, these boundaries are exposed like pages torn from the Earth's diary. Even color matters. Reddish-brown rock indicates iron oxidation, often associated with hydrothermal activity. Pale, bleached zones suggest chemical alteration. Greenish stains may hint at copper, which often travels alongside silver and gold. None of these signs guarantee metal, but together they speak. Deserts do not whisper loudly, but they never lie. And here is the symmetry most people miss. Where you find gold indicators, silver is rarely far. Where silver spreads wide, platinum often lies deeper nearby. Different depths, different expressions, same origin story. This is why some desert regions produce all three metals over time. Not at once, not obviously, but inevitably. The Earth does not waste effort. When conditions are right for one, they are often right for all. Deserts did not always look this way. What appears dry, lifeless, and still today was once shaped by water, pressure, and motion on a massive scale. Long before sand dominated the surface, rivers carved through rock, oceans advanced and retreated, and mineral-rich fluids moved freely beneath the crust. This matters because gold, silver, and platinum are not just products of heat and pressure, they are also products of movement. In many desert regions, ancient river systems once carried enormous energy. When climate shifted and water vanished, those rivers didn't disappear completely. Their paths hardened into stone, their beds became dry washes, their curves became silent traps. And heavy metals never forget gravity. Gold, silver, and platinum responded to those ancient flows exactly the way physics demands. Gold dropped first, heavy and decisive. Platinum followed, denser still, sinking deeper into natural depressions. Silver traveled farther, lighter and more willing to scatter, coating surfaces and seeping into fractures. Today, deserts expose these systems without disguise. Dry washes, arroyos, and paleochannels, ancient river paths now frozen in place, are among the most honest geological storytellers on Earth. They reveal sorting, they reveal concentration, they reveal symmetry. When you examine a desert wash closely, the clues are subtle but consistent. Heavier material concentrates on the inside bends. Black sands gather where motion once slowed. Angular quartz fragments indicate proximity to source rock, while rounded stones suggest long travel. Platinum often hides here, not visibly but physically. It resists weathering. It survives where lighter minerals are carried away. Gold behaves similarly, though it often lodges slightly upstream, caught in cracks and natural riffles formed millions of years ago. Silver, meanwhile, leaves its presence in the walls. Oxidized silver minerals stain surrounding rock. Faint grays, dull greens. Sometimes barely perceptible unless the light hits just right. In desert sun, those hints are not washed away. They remain preserved, waiting. This is why desert prospecting rewards patience over excitement. Shiny distractions fade quickly here. Structure endures. Another critical factor deserts reveal is contact zones, the boundaries where different rock types meet. These are not just geological curiosities. They are stress points, pressure changes, chemical reactions. Gold and silver love these boundaries. Platinum respects them. When magma intrudes into surrounding rock and cools, it creates a chemical conversation between host rock and intrusion. Metals precipitate along these borders, especially where fractures allow fluids to move repeatedly. In desert terrain, contact zones are exposed cleanly. You can often walk them, see the color change underfoot, feel the density shift, hear the sound difference when stone strikes stone. This is not romantic language. This is physical reality. Rocks formed under different conditions respond differently to erosion. Deserts strip away the softer layers and leave the harder truth behind. Ultramafic rocks, dark, dense, magnesium-rich, are especially important for platinum. They weather slowly. They stand out. They feel wrong in the hand, heavier than expected, colder, resistant. These rocks are rarely appreciated by casual observers. They lack shine. They lack beauty. They lack obvious reward. Yet they are among the oldest materials on the surface. Time favors density. Gold's relationship with deserts is equally revealing. Because deserts do not replenish sediment quickly, placer deposits remain stable for extraordinary lengths of time. Gold that settled millions of years ago may still sit within inches of where it first stopped moving. This is why deserts can hold wealth that appears untouched, not because it was ignored, but because it was never visible to those who didn't understand the signs. Silver behaves differently over long desert timelines. Because silver oxidizes readily, it often forms secondary minerals near the surface. These minerals can leach, redeposit, and stain surrounding rock repeatedly over thousands of years. Deserts preserve these cycles like layers in a book. One stain means little. Repeated alteration means history, and history is where symmetry becomes undeniable. Gold, silver, and platinum respond to the same stress events: tectonic shifts, magmatic intrusions, erosion cycles, climate transitions. They separate by behavior, but they reunite by cause. This is why regions known for gold often later reveal silver. Why silver districts sometimes surprise with platinum. Why the Earth rarely offers one without hinting at the others. Symmetry does not mean equality. It means alignment. Even wind plays a role here. In deserts, wind acts as a sorting mechanism, slowly removing lighter material and leaving heavy components behind. Over centuries, this creates lag deposits, concentrations of dense minerals at the surface. Gold can appear this way, platinum even more so. Silver's contribution is subtler, but it often marks the zones feeding these concentrations. These processes are quiet. They do not announce themselves, but they never stop. This is why understanding geology restores patience. You stop chasing excitement. You stop expecting instant reward. You begin to read, and reading the land changes how you think. Not just about metals, but about value itself. Gold, silver, and platinum are valuable because they obey rules that human systems cannot break. Scarcity, density, irreplaceability. Time. They do not respond to trends. They respond to physics. Deserts teach this lesson better than anywhere else. Nothing is hidden behind excess. Nothing is softened by growth. Nothing is disguised by comfort. What remains is structure, and structure is where truth lives. As we step back and look at the symmetry between these metals, how they form, where they settle, how they reveal themselves, We see something deeper than geology. We see consistency in a world that pretends to be chaotic. Gold anchors value, silver spreads function, platinum enforces necessity. Different roles, same foundation. This is why civilizations return to them again and again. Why modern systems still depend on them. Why deserts, silent, patient, exposed, continue to hold answers most people overlook. And this brings us to the truth most never hear. The earth does not hide wealth to be cruel. It hides it to be selective. Only those who slow down, observe patterns, and respect structure are rewarded with understanding. Not excitement, understanding. Because when you recognize the symmetry between gold, silver, and platinum, you stop asking what is valuable. You start asking what is inevitable. And inevitability, whether in geology or in human systems, has always been the most reliable signal of all. This is not about finding metal. It is about learning how the earth thinks. And once you understand that, deserts are no longer empty places. They are open books, written in stone, patiently waiting for those who know how to read. They say nature never hides treasure in something beautiful. Sometimes the ugliest, most unassuming rocks conceal the world's most valuable metal. Gold. It doesn't glitter on the surface. It doesn't shine from the cliffside. It hides beneath layers of grime, sharp textures, and a skin so unattractive that most people walk past it without a second glance. But what if I told you, those rocks you ignore might be your ticket to unimaginable wealth? Welcome to the secret world of the rocks that guard gold. Today we're going to dive deep into one particular rock that's been called ugly, common, and worthless. Yet time and time again, it proves to be the ultimate gold-bearing monster. It's the one that prospectors chase through jungles, deserts, and riverbeds. The one that ancient civilizations recognized, long before we understood its secrets. And the one that could be sitting right beneath your boots. This is the story of the rock that hides gold, and how to find it before anyone else. Let's start with an uncomfortable truth. Most people looking for gold are looking at the wrong rocks. They search for glittering quartz, shiny flakes, and flashy minerals. But real prospectors know gold doesn't advertise itself, not at first. Instead, it partners with rocks that are tough, grimy, and ignored. And one of the most overlooked of them all is iron-stained quartzite and gossan. To understand this rock's role in hiding gold, we have to go underground. Gold isn't just found lying on top of the earth. It comes from deep within the crust, transported by hydrothermal fluids over millions of years. And as those mineral-rich fluids move upward, they deposit gold into veins that are sealed inside rocks that look, well, disgusting. Gossan is a type of oxidized, weathered rock formed when iron sulfides are exposed to air and water. It's rusty, it's reddish-brown. Sometimes it even crumbles like dry cake, and it forms right above gold deposits. But why? Because gossan is a byproduct of something deeper. Sulfide-rich ore bodies, the kind that often contain not just gold, but silver and copper too. When sulfide minerals like pyrite and chalcopyrite oxidize, they leave behind iron oxides and hydroxides, like limonite and goethite, which stain the rock surface red, yellow, or brown. That ugly crust is your biggest clue. Seasoned miners call gossan the iron cap, the surface indicator of treasure below. It may look like nothing, but underneath it often grades into richer and richer ore. Now here's where it gets more interesting. Gossan often contains boxwork textures, hollow cavities left behind by dissolved sulfide minerals. These honeycomb-like patterns are like nature's roadmap to gold. If you see them, take out your hammer. You're in the right place. Because Gossan doesn't look valuable. It's coarse, dull, and rusty. It doesn't sparkle like quartz. It doesn't shine like mica. And it doesn't have the smooth elegance of polished gemstones. But its value is in what it hides. The next time you find a rock with jagged edges, reddish streaks, and a hollow core, don't throw it aside. You might just be looking at a piece of the Earth's most ancient gold vault. Let's talk about where you can find this rock. Gossan often appears near fault lines, shear zones, and hydrothermal vein systems. These are areas where the Earth's crust has been shattered, reheated, and mineralized. It appears in mountain foothills, where erosion exposes old rock desert ridges, where iron stains contrast against pale sands riverbanks, where fragments break off from larger deposits upstream. And here's the trick. Gossan forms on the weathered top of the deposit, so if you see it, gold might be directly beneath your feet. Now let's get even deeper. Gossan isn't the only ugly rock that hides gold. In fact, some of the ugliest, blackest, most oily rocks you'll ever see also point to gold's presence. Enter black shale. This organic, rich, sedimentary rock might look like burnt toast, but its carbon content plays a role in concentrating gold from surrounding fluids. Gold loves to bind with organic matter. In some regions, black shale layers act like sponges, soaking up mineral-rich fluids and locking away gold. Black shale is often layered, brittle, and crumbly. But when you break it open and spot sulfide specks or smell that subtle sulfur scent, you're onto something. In parts of Canada and Africa, black shale zones are directly tied to gold-bearing formations. And just like Gossan, they're often ignored by amateur prospectors. And then we come to the next suspect, serpentinite. Greenish, waxy, and twisted. Serpentinite looks like something dredged up from the ocean floor, and sometimes it is. It forms from the alteration of ultramafic rocks deep in the mantle. And although it doesn't carry gold on its own, it's often associated with gold-bearing quartz veins, especially in places like California's Mother Lode. What makes serpentinite special is its tendency to host fault zones, perfect conduits for gold-carrying fluids. When those fluids find fractures in the rock, they deposit quartz, and within that quartz, microscopic gold. So even though serpentinite looks alien and unattractive, it's a geological signal that tells experienced miners. Gold may have passed through here. Let's take a breather. So far, we've learned that ugly rocks like Gossan, black shale, and serpentinite often point to gold. These rocks form in environments where gold-carrying fluids concentrate. Their appearance, rusty, black, greenish, is a natural camouflage. But what happens when these rocks break apart and travel? That's when the real hunt begins. What appears to be just another cracked, unsightly rock, often coated in dull greenish hues or smeared in mud, can, under the right conditions, erupt with veins of raw, yellow treasure. We're about to explore the hidden worlds inside these rocks, how they trap gold, and, more importantly, how you can spot these subtle signs before they vanish under your very feet. Let's start with a rock that's both feared and revered in the gold hunting world. Arsenopyrite. On the outside, it looks like a metallic lump gone wrong. Its flaky silver-white sheen can be confused for worthless pyrite, but crack open a rich sample, and you may find streaks of native gold running along its fractures. It's not just ugly, it's toxic if mishandled. Yet in many high-yield mines, arsenoporite is the key indicator of gold. Now let's pair that with a second deceiver, iron-stained quartz. At first glance, it may resemble rusted gravel tossed from an old construction site, but the rusty hue is often the result of oxidizing iron sulfides, which can lead miners to nearby gold veins. That reddish-orange stain isn't just dirt. It's the history of hydrothermal fluids escaping and leaving behind more than just color. But gold doesn't always travel alone. In the crust, it hides in the company of unlikely companions. Serpentine rocks, for example, are famously unattractive. Greasy green, slick-looking stones that were once part of the Earth's mantle. In California's Mother Lode, in parts of Ethiopia's Adola Belt, serpentine zones have become geological gold corridors. They crack and fracture easily, allowing quartz veins to infiltrate. And where quartz goes, gold often follows. Let's step into the world of schist, another homely, flaky rock, often mistaken for worthless slate. Its banded appearance, shimmering in silvery or bronze reflections, may not catch the eye of a casual hiker. But for a trained prospector, schist is gold's hiding blanket. Its high mica content and layered structure offer perfect fissures for molten quartz to deposit. And if the temperature and pressure align just right, gold settles in, quietly, stubbornly. But what makes these rocks such powerful vaults for gold? It's not about beauty, it's about structure, chemistry, and pressure. These ugly rocks are survivors. They've been bent, cracked, cooked, and fractured, creating passageways and pockets where hydrothermal fluids carrying dissolved gold can seep through and cool. The uglier the rock, the more tortured its history. And ironically, that tortured history is what makes it such a rich target for gold. Take gossans, for instance. These rusty, blistered crusts form above sulfide deposits. They're blistered and broken, looking like burnt sponges. But gossans are nature's flare gun, signaling that valuable minerals, including gold, lie deeper below. In Western Australia and Nevada alike, gossans have guided some of the largest gold discoveries in history. Still, you must train your eyes for more than just color. Texture, fractures, and location all matter. A rock with radial fractures, often surrounded by discolored clay or iron oxides, may be a sign of past hydrothermal activity. And what lies just beneath these textures can be mind-blowing. Imagine splitting a seemingly worthless rock in two and finding gold leaves nestled like ancient scrolls. This is not myth. It's the real, raw moment many field geologists and artisanal miners have faced. Now let's talk about geological traps, the structures that hold gold in place within these ugly rocks. One of the most important is the fold hinge zone. Rocks that have been folded under pressure form tight, compressed creases. Gold-laden fluids often concentrate in these hinges. From the outside, these zones just look like chaotic rock masses. But drill through them, and the results can be astonishing. Similarly, fault zones and shear zones are messy, disjointed, fractured bands of rock that, to the untrained eye, appear broken and useless. But they act as gold highways, allowing fluids to move, minerals to deposit, and veins to crystallize. Many modern gold mines are centered entirely around these disfigured, misshapen corridors. And don't underestimate breccia, a jumbled mass of angular rock fragments fused together by mineral cement. It's geological wreckage, but beneath the chaos often lies gold. In fact, some breccia pipes are so rich, they've turned once-ignored prospects into major extraction hubs. Then there's laterite, especially prominent in tropical gold belts. Laterites form from intense weathering. They're reddish, crumbly, and often dismissed. But beneath this rusty soil may lie remnants of gold-bearing lodes that erosion and time have tried and failed to erase. But spotting these rocks isn't just about science, it's about timing and terrain. After heavy rains, gold-bearing rocks get washed, revealing new faces and fractures. The mud slips away, the iron stains glisten. Sometimes gold itself peeks out in glints. Riverbanks, stream beds, cliff faces. These become your treasure maps, redrawn by each storm. And while panning and metal detecting remain essential tools, the true advantage lies in recognizing the rocks others overlook. Because that ugly rock, it might not just hide gold, it might be the very lock that guards a geological fortune. Before we close, let's reflect on something powerful. Nature hides its finest treasures not in glitz, but in grit. Gold often nestles itself within the folds of rocks that look broken, battered, or worthless. These are the survivors, the remnants of Earth's violent, molten past. So the next time you come across a rock that looks too ugly to matter, take a moment, check its weight, scrape its surface, examine its cracks, because deep inside that rough exterior may lie the story of 1,000 years and a treasure waiting to be discovered. Sometimes the most unremarkable stone is the one that will change your life. So next time you step over a cracked, muddy rock, pause. That ugly lump might be nature's dirty little secret. Because when it comes to gold, beauty lies deep beneath the grime.